So we'll carry to review our multiplicative weight update method, see one or two examples, and then move, see the difficulty, how do we in applying this to streaming algorithm, things like that. But notice what you learned last time. You learned last time to solve LP almost approximately. Like very large families of LP we can solve approximately given that oracle, and which is not very hard to make in most cases of the applications we need. Okay, because okay, so the theorem which we proved last time was as follows. Okay, so what did we prove last time? The theorem which we actually proved, let's write it down. Okay, let epsilon greater than 0 be a given error parameter. Okay, okay, given error parameter. Okay, and suppose there exists L row oracle, right, which basically, I mean, I give him a constraint, one constraint, right, remember, which is basically a linear combination of these probabilities. Okay, I'll come to that. Okay, suppose there exists a L row bounded oracle, okay, L row bounded oracle, okay, uh, for the feasibility problem. What is the feasibility problem? So look, the kind of covering problem we were trying to look basically was, if you recall correctly, we asked ourselves, does there exist a x in some polytope? Okay, does there exist question mark x in the polytope, some polytope, okay, such that Ax is greater than or equal to some vector b. So this is the kind of problems we were trying to consider, like feasibility problem. And I told you that we could make this, we could solve optimization problem by guessing the value and putting that constraint that, oh, if it is a maximization problem, then I should say it should be at least this much. If it is a minimization problem, then I will say at most this much. Okay, depending on what conditions do we have. Okay, okay, so this is what our, and what did I told you? So, and what is the oracle we are talking about? The oracle we are talking about is that you are given a probability vector, given a probability vector p, right, over your constraints. Okay, what we wanted to say, ask vector p on m constraints. Okay, there are m constraints here. Okay, and what you wanted to say, we wanted to ask, does there exist x in p which satisfies what? P transpose Ax is greater than or equal to P transpose B, right? This. And this basically, by doing this, what have we achieved? We have achieved that we have managed to merge all the constraints into one, right? So this is all that we wanted. And in some sense, whenever we said L row bounded oracle, for now, if I all had to say that it's a row bounded oracle, okay, okay, then all I can say that for each of the constraint, what is the property that we would like to have, right? Basically, ai minus x, right? ai x minus x minus bi is less than or equal to 2, right? And but when we had this L row bounded oracle, then basically we had a lower bound and upper bound. So L is less than equal to rho, okay? And then we said, and for a subset I, okay, for a subset I, what we wanted for all I in I, we wanted that AIX minus BI, AIX minus BI is less than, is element of minus L times rho, and for all I not in I, it is AIX minus BI is element of minus rho comma L. Okay, but for now, just to keep in mind, all I'm telling you that look at how much it is violating, how much each constraint is violating, right? This is basically, think of this violation. So the violation is bounded. It is not unbounded violation, right? I have been able to set the values of x such that the value of AX and BI doesn't differ from each other, but by factor rho. It could be under or it could be above, but this is all that it is, right? So in other words, AIX minus BI is less than equal to minus, so greater than equal to minus rho and less than equal to rho, right? So I have a current vector x which almost satisfies this, but we have still not got. So basically, we have a window and we are trying to come down, and at some point of time we want to prove something interesting, okay? Okay, and then we saw this trick that for lots and lots of problems, if I can say for all I, AIX minus BI is greater than equal to epsilon, right? Or is greater than equal to, say, at least B minus epsilon, BI minus epsilon, then we could just multiply by 1 minus epsilon and take care of this. This is what we said. Did we say this? No. I thought that we said that if every constraint is under, like if the value is at most 1 minus epsilon, then we can get a feasible solution. Yeah, this is what, right? So we said that, okay, then multiply by 1 minus epsilon everywhere, and somehow we were able to do this. It satisfied this, right? Times BI, this is what we said, okay, which is fine. BI times epsilon times BI. This is how it should be, right? Then we can divide by 1 minus epsilon and take care of everything. Fine. So this is the model we have been working with, okay? And what we managed to prove that, look, this is really a very quite a generic packing covering LPs, right? And what does this tell us? That we can get a value very closer to the optimum, right? In like combinatorially. We do not have to solve simplex or solve iterative like interior point methods and all this to solve this LP, right, which you are learning in LPCO. So this gives an alternate way of, and in many cases it achieves much better running time to solve these combinatorial LPs than whatever you will be able to achieve via interior point method, or there is something else also, ellipsoid, okay. So in that sense, like this should be actually taught to the LPCO course. It shouldn't be taught in streaming algorithm course, in my opinion. And this is actually taught in like linear programming and optimization course everywhere else. Okay. Okay. So given now that you understand that what do we mean by this terminology here, I have revised them for you. So say oracle for the feasibility problem, and what was the feasibility problem? So the feasibility problem is basically this. So for this, if you gave me some value of x, right, then what does it tells us? Feasibility problem. Now it says assume that L is greater than or equal to epsilon by 2, okay. Then either then there is an algorithm that either finds what is that called? Either finds x such that for all I, ai x is greater than or equal to actually bi minus epsilon, okay, bi minus epsilon. Fine. Or correctly concludes that the system is infeasible, okay, like the in the beginning system is concludes that the system is infeasible. Okay. Okay. And what is it? So look, what did this algorithm run? This algorithm went into rounds and rounds and rounds, right? Right? Each round it updated some weight vector and some probability vector, right? So the one question is, how many rounds will it take before it achieves such kind of guarantee? And what did we show? We showed that the algorithm makes only how many makes only big O of L and rho log m epsilon square, what do you call epsilon square calls to the oracle, okay, with an additional pre-processing time of oracle. So what will the running time, if I really suppose if I can, if the running time of the oracle, it's a running time of oracle is say t oracle, right? Then the total running time of this algorithm is going to be O t oracle times precision factor epsilon square log m, and for what L and rho you are able to make such oracle, right? So this is what the running time of the algorithm will be. Okay. Now, what is known is that suppose A is a positive matrix, A is not negative, like A is completely positive, right? Because I have not assumed anything. All I am saying that A is in R m times n, right? But for example, if you assume that constraint matrix A is all positive, okay, if we assume that constraint matrix is all positive or all negative, not mixed, then, and this is a homework, okay, then we can actually then if we have row bounded oracle, okay, then we can achieve order. So look here, basically if it is row bounded oracle, it's rho square log m by epsilon square. You can reduce it to rho log m epsilon square. Okay. Because what happens if you have covering problems? So then you're basically saying minimize C transpose X if you have a covering problem and AX is greater than or equal to B x greater than or equal to 0. This is what it is, right? This is a covering problem. This is what is called covering problem. I want to cover some things, right? And suppose A is positive. What can we do? Right? You can scale this B, guys, in a way that all you will be, you can write it down, it is same as minimizing C transpose X, Ax is greater than or equal to 1, x greater than or equal to 0. Okay. Okay, they are equivalent. Of course, you have to multiply with the scaling factors. So, what will the scaling factor? Okay, please figure it out. This is exactly what the homework is. Okay, but if this is the case, we can get rid of one dependence on our row. That's all that I wanted to make a point. Okay, so now let's see how do we apply all these things in one concrete example, and then we will move to. Okay, so suppose I had a fractional set cover. Okay, so let's just to make our hands dirty, let's solve fractional set cover. What? B, there's no assumption. I don't think we need any assumption on B. Okay. Or maybe some epsilon away or something. Okay, anyway, think about it when, what does it mean, okay? Okay, so now I would like to use this lemma and let's do one concrete problem, actually two concrete problems, let's see. What happens to, what will we achieve? Okay. So suppose I want to find fractional set cover, and then we will see how we can apply probability to even integral set cover. Okay, so what is the set cover LP? So I want to solve set cover LP. This is all that I'm trying to tell you. So what is this? I have to minimize summation xs, right? And suppose I have a family F of m sets. Okay, I have a family F of m sets. Okay, and what do we have to do for every element in the universe? And I have universe, right? What is it? For all S which contains E, right? We have to write xs is greater than or equal to 1 and xs is greater than or equal to 0. And if xs is an element of 0, 1, then this becomes ILP. Okay, but we are only interested in solving fractional LP, which is close to this value. Okay, so look, for now I have just chosen integers, like there are no weights. So what I know on minimization of this, I know that summation xs over s, right, is actually upper bounded by n. You don't need more than n sets to cover all the elements. So this is like, we know this. Optimum value cannot be more than this, right? Because for each element I just go and pick a set and just set this to 1. Definitely this is feasible, right? Right? This is a feasible solution because for every element I have just arbitrarily picked one xs. But how many sets I have picked? N sets, right? So, and rest I picked 0. So this is definitely a feasible solution. So clearly, if I want to do minimization, I can only do better. Okay. So now I can do binary search here. Okay. So for now, let's assume that, or if you don't want to do binary search, assume that I do 1, 2, 3, 4, 5. Okay. So suppose opt is equal to L, okay, which is in 1 to M or 1 to N. Yeah, I don't know why this is saying 1 to N, but okay, doesn't matter. Something, right? Opt is L, which is between 1 to N, right? Now, so the polytope we are going to consider is K. So what is the polytope we are going to consider? So the polytope over which we are trying to find a solution, what is the property? The property is that for some S, xs equal to L, right? Xs greater than or equal to 0. So this is what my polytope is over which I am trying to find a solution, right? And so what we want to do? We want to find x in k, okay? We want to find x in k, okay, such that say what is this constraint called? Such that plus plus constraints are satisfied. Am I right? That's my goal. Okay, I want to find x in k. But to solve this, if you remember this algorithm, first let's make an oracle for this. Because what was the algorithm actually doing? Algorithms needed, if you recall correctly, what was the algorithm doing? So let's, we went round and round, okay? So to t, okay? We said let x of t equal to 1 to t be the solution returned by the oracle, okay, by the oracle with respect to values. What was the values? We said, well, look at the weight at the tth round of the first guy and summation phi t, weight of whatever it is. So in our set it will be, because no, we will have how many experts? N experts, right? So it will be N phi t. If there are, how many constraints we have? N constraints. Yeah, we have N constraints. Okay. So this is what we were doing, and what was phi t? Was basically summation of weight I of t, okay, I going from 1 to n. This is what it was. So this was basically acting as a probability vector, which we set what? So initially, so this act as your probability vector p of t, and in the beginning, what did we set? W1 of 1 equal to 1, Wj equal to 1 for j equal to 1 to n, right? So in the beginning, we are just uniformly at random choosing, because like 1 by n, 1 by n, 1 by n, okay? And then we defined the cost vector, like how much we are going to penalize these people, okay? And what was that? So in ith, for the ith guy, we penalized him with ai x t, returned minus bi, and we divided by, what did we divide by? I think we have to divide by eta, right? Okay, but what is this row? This row or this row bounded row? Okay, so this is what we defined for all these guys, right? So this is how we define MIT. And what was the weight upgrade? If you recall, weight upgrade was Wi t plus 1 was Wi tth round 1 minus MIT eta, and you remember we set eta is less than or equal to half. This is, isn't this figuring somewhere here? Maybe it doesn't figure. Okay, so eta is less than or equal to half, right? This fixed in the beginning for our algorithms. Okay, so this is what we did. So these were the basically steps of the algorithm. Okay, did this, did this, did this. But to do all these steps, right, all I need, so this is what the algorithm does, but for him to do something, he needs to get this oracle and the bound, like what row bounded oracle it is. But to do that, what we need to solve? We need to solve, so whatever the probability vector is given to me, right, P transpose, right? So what I have to show to you? I have to show to you that, so given some P, okay, it tries to find X in K, okay, such that what happens? Look, what do I need it? So if you recall correctly, we said, well, it is P transpose AX should be greater than or equal to P transpose B. This is what we said, right, for any probability vector. Now, whatever maybe this probability vector is, what is B for us here is all ones, right? So whatever they say, this should be greater than or equal to 1, because look at P transpose and B. This is actually P transpose B, because B is all one vector, this is exactly equal to 1 in our case, like in for us, because you're just summing up all the probabilities, which is equal to 1. But here, think of this way, look at each constraint. Here it is your matrix A, which is n cross m matrix, sets S1, S2, Sm, and basically for every element, if that guy is present here, you, like, it's basically, it's a characteristic vector for E with respect to this S1 to Sm. Whether if he is present here, then I put 1. If it is not present here, put 0. And this is exactly what this constraint is, like for summation E in S, Xs is greater than or equal to 1, which just means that you look at this and take x1, x2, xm. So when this guy and this guy will be 1, when exactly at those places when E is an element of S, but at that place this is 1. Right? So basically it is characteristic vector of element with respect to S1 to Sm, right, and multiplying. This is all that we are doing. Okay, and now what does this tells us? This says, okay, you also multiply this with P1, P2, Pn, right? So what is P1 multiplying to? P1 is going to so if I multiply this way, then basically it is summation Pe over every element, because, right? So this is basically it is times, so what I mean to say, forget now and multiply this. What are you going to get? You're going to get this into x1, like look at n cross m and this is m cross n matrix. What are you going to get? A vector which is m cross 1. No, n cross 1 vector, right? And this is also n cross 1 vector. So I can think of this as just, and then first if I multiply this and then I multiply with this, then this is nothing but what? P1 times the sum, P2 times the sum, P3 times the sum, and so on and so forth. So I can write it down times, how to, okay, so let's, or rather I would like to write, let's say it's, okay. So basically what is happening? What is happening is you are looking at P1, right, and you are multiplying all these guys here, right, all these guys, right. P2 actually, so P2 actually multiplies to everybody here, P3 multiplies to everybody here, P4 multiplies with everybody here. So basically this I can write summation over E, PE times what? Times this, right, summation E in S, so I fix PE, PEE in S, XS. Do you agree? This is exactly what it is. Like this, so if I take this, so this into this is my first term. So, right, so after I have taken this sum, what is this? Basically, if you look at this sum, this is basically this summation E in S, XS, and blah blah blah. So you will get this n coordinate, and now I am multiplying with this. So P1 times this, P2 times this is like a dot product. So it's summation taken this. So this is what it is. Now I want to rewrite this with respect to S. Then what is this? Well, how many times S XS vector will be counted? For each element once. So I can write it over S, I can write it over all, going over all S, XS times summation E in S, P, if and only if this. This is exactly the same quantity, right? So here for every element which all sets you appear. Now, which is same as I go over all sets and I go over all elements which belongs to this set. They are same thing. So you were counting like this, now you count like this. That's it. Okay. Okay. So let's use this space to understand what is happening. Okay. So now I'm going to define a quantity for S. Let's define P of S is summation E in S, P. How do I write P? Okay. This is like sum over all probabilities of the elements in that set. So then I can write this summation over S, XS times P of S should be greater than equal to 1. So when will this quantity be maximized? When will this quantity be maximized? Like each individual term. Each individual term will be maximized for by just concentrating on a set with the maximum weight. No? No. Look at this quantity. For which one this will be maximized? I have excess, right? Already I have been, look, you have to assign excess, like you have to assign excess, right? So if I concentrate on a set with a maximum weight or maximum probability, so think of PS as probability, if I somehow concentrate on that, then clearly and set this guy in a way that, so for example, I could set look, I also have to be set something inside here. I have to find a point here, right? So what happens if I set xs equal to L for some s in F that maximizes P of S and 0 for all other s? Okay. So what I want to do, so let's look at this. Okay, I would like to leave that. This is not useful space. Okay. So this is what I would like to space, right? So this now has become some sort of maximization problem, right? Because if I find a maximum value of this, given this constraint, right, then clearly if that maximum value is strictly less than 1, I can say infeasible, right? But if I can find something which maximizes this, clearly this is some feasible solution, but it is perfectly fine because we are under this constraint, right? But that doesn't mean the solution which I am going to give you is going to satisfy all plus plus, right? And that is the whole point of this, right? So we remain in this world of constraints. We are satisfying somehow the value in a nice way, but we may not be satisfying the constraints at the time. So we go over this. This is what this was doing. Oh, I have an assignment which is able to satisfy these constraints properly. Forget about those constraints. And how did we achieve this? By penalizing those constraints or penalizing those experts. It's like, oh, you are a costly expert, I shouldn't be using it. And that is proportional to how well the guy had satisfied, because so that I can concentrate on other set of constraints which are still under satisfied. Okay, so this is what it is all about. Now, okay, so this quantity, if you think about it, is clearly maximized when we concentrate over set that maximizes P of x. Okay, now we will set following. Let S be a set that maximizes P of S. There could be many sets for which P of S is maximum. Just choose one set. Okay, let S be a set. So now what is this? Xs equal to L. What the L is? This is this L. Okay. If okay, not right. X W equal F, W equal to S, 0 otherwise. This is my assignment. So what is the width of this? What is the width of this assignment? What is it, like, remember, we have to show that AIX belongs to the, like, value is not too much. Fix any set, right? We have to show, right, that by doing this, no set is under or over by too much, right? That is what this row is. Huh? It's L minus 1. Why? Let's look at this. It is not very hard to see. At least this fact is not very hard to see. Okay. So you fix any, okay, fix E in S, like fix a constraint in S. Now summation E in S excess, right? So there are two cases. Either the either the like I think, let me write that S hat that maximizes B S hat, S hat. Now look, either S hat is contained here, right? Either S hat is contained here or S hat is not contained here. If S hat is not contained here, then what is its value? If E does not belong to S hat, then what is the value of this? This is equal to 0, right? But what is the right hand side? Is 1. So what is this? What is AI x minus, look, right? This is what we were dividing by rho to get the cost, right? How well you are satisfied. So this is what our oracle was doing, right? Where did I wrote? I robbed my oracle. This is what happens when you are working in a small. Right? So what is this belong to? Look, what was we trying to say? We said for all I, AI x minus bi should belong to something and something. So if this is the case, then this belongs to where? What is AI x minus 1? So this is actually, if E hat is not in this, then this is equal to actually minus 1. Right? Okay. Now let's look at, so what did we get? If E is in S hat, then AIX minus BI is equal to minus 1. No issues. Not in S hat. Okay. Now suppose E is in S hat. Then what is its value? Huh? At least this value is exactly equal to L. So in that case, what is the value of AIX minus BI? Is L minus 1. Right? So what did we, so if L is larger than some 1 or 2 or whatever it is, so what bounded oracle is this? Right? What bounded this oracle is? If there are, I mean, I can clearly say this is less than equal to n minus 1. Which is less than equal to n. So clearly it's n bounded oracle. But there's one more question to be understood. Is this equal to L? Why? I set one set equal to L and rest set to be 0. There was no, probability is not here. So my x is indeed inside K, right? I cannot give you any x which is not inside this. So I have given you an x which belongs to this place. So this is how you find your, so I have given an L bounded oracle where L is like n. So now if I do this algorithm, L and rho for now, suppose it is. So what is L here? If I would have tried to make L rho bounded oracle, then L is like 1. But no, No, L is 1. This little L is 1. So suppose I wanted this oracle, but I don't know which I, and my I is everything. Like I select I to be everything. Right? So it is between -1. Notice. Then this is between what? So for all I in I, what did it say? It said that our oracle should have some property. What was the property? It should be between minus L. Yeah, minus L comma rho. So I will fix my rho equal to capital L in this, and this little l equal to 1. Clearly every set is between this and this, because what did it tell? Right? There is a fixed subset I subset of M of consists that whenever the oracle manages to find a point x, there is some fixed set, and that fixed set is whole all the constraints. So clearly this is there, right? So now you see how one L will go away. Right? This is true about almost, this is true whenever this was 1, but when you have other vector like b and this and that, you have to be careful. This is why I was trying to do a scale up. Okay, so what does this tells us? Okay, this tells us that I can find a LP solution to this, right? LP solution to this under this constraint, that it is equal to this, but it will not be feasible. My solution will not be feasible. You understand? So now suppose I solve this LP, right? So definitely whatever the final I am going to get is going to be equal to L, and what is after I run how many times? Big O, what is L here for me? N, right? Log M by epsilon square plus M, right? Because say time of extra pre-processing time of order M. So okay, so fine. So plus M. So after this much time, and then forget this M, because anyway there is log M here. No, I cannot forget it. So let's write it down. Because okay, after this much amount of time, what did we get? We have got a vector x with what is the property of that vector x? Let's try to understand the property of that vector x. Okay, what is the property of that vector x? If you read from here, so and how much time will this oracle will take? So this is okay. So this is why we should write plus m. Okay, outside times, because this is these many times to call to the oracle. This is fine, but how much time does it take this oracle for implementation? Linear time, like at most n plus m time, because what is not even n plus m time. What does it need to do? Nothing, right? It looks at the probability vector, right? Looks at which, goes through every set, looks at which set has the highest probability vector, right? Sum of this, right? So it will take, actually it could take m into n time, because you might so what I'm saying that for every set I need to compute P of S, right? So in the bad case I could take n into m time. Fine, I take n into m time. But now I can forget this because I'm taking so much time. But in this much time, what have I given to you? I have given to you some XS value, some XS value like XS1, XSM. What is the property of them? Their summation is equal to L, because I was always doing with this. And now this is an optimum value, so this is perfectly fine. Otherwise, look, I'm trying to maximize this constraint, right? So I try this, I take the next to L and then do some sort of binary search over L, right? It will take some log n. So you also need to write another log n to do binary search for L, right? But now let's look at what does this guarantees mean, right? For all I constraint aix, whatever, let's call this vector x vector, right, is greater than equal to, but do you remember what vector did we return? Look, at the end I was doing this, but at the end this is not the vector you return to the algorithm. So what algorithm do you return? So you cannot return any of the xt. In the proof, we did not return xt. What did we return? Because xt is advantageous to some constraints, right? Look, if you recall the proof of this, we did not return xt, the last, but we returned 1 by t of summation xt. So that it is like on an average, you are, look, in each iteration we took some constraint which were under satisfied and tried to satisfy it. So xt was also doing that, right? So that solution is advantageous to these set of constraints but may not be to the other. So you take the average of all this, and that is what we were able to show last time. So it's basically summation x bar, this is what we returned last time, t equal to 1 to t xt divided by t. So it's the average. So this is what you return. So this has all these properties. So I mean, just look, because you might get confused that, oh, last thing which we have is what we output. No, last thing you do not output. Okay? Okay, good. Right? Just, and why we are doing this? So you have a good, what was my whole strategy? I'm trying to satisfy my constraints on an average. That's the first thing. That is what I'm trying to do all the time. A. In each round, we concentrate on some set of constraints which are under satisfied, right? So the last round, when we say, okay, no more, we are ending now. What is the property? It would have also tried to satisfy some set of constraints. So what you have done now is that, okay, fine. Look at the first xi, it was trying to satisfy some constraint. So overall, in together, they were trying to satisfy all the constraints, and I take the mean of that. Okay. Okay. But now what is the property of this each EAXI? That this is greater than equal to 1 minus epsilon. Bi minus epsilon. So this is greater than equal to 1 minus epsilon, right? So now whatever I have, if I take xsi equal to 1 minus epsilon, then I'm definitely feasible solution to everything. But now my opt, which was like L, is how much? So in the before, my value, should I divide by 1 minus epsilon, or yeah, I have to divide by 1 minus epsilon. So what is my new value? Is going to be L divided by 1 minus epsilon. So you are slightly far, like you are not satisfying your LP value, which you can solve exactly, right? It's a 1 minus epsilon approximation to your LP. This is how you should view it. Okay? Okay, good. So we know how to solve fractional set cover. And look, the reason why I did set cover, because this is a very generic thing to do for any packing covering objects, right? Right? Okay. So can I write my matching as like some kind of covering constraints? Do you know how to write down? Okay? Okay? Or maybe I should do set cover before I do matching. Let's do, so this is fractional set cover. Now, what does greedy set cover algorithm does? The greedy set cover algorithm does, if you notice, which has log n approximation algorithm, is following. It tries to find set that satisfies the maximum number of uncovered elements. This is a greedy heuristic. Am I right? So the greedy heuristic for set cover is, okay. So now I will rub. So now you understood how to do such an example for set cover and set things up. Okay. So let's write down the greedy algorithm first, okay, or the greedy heuristic. So this is a very big thing when, so using this method, you can approximate not only linear programming, also semi-definite programming, right? And this is the reason why many known like rounding algorithm became like independent of all these solvers, and people optimize everything because it's something which solves very generic object may not be optimizable to give you good running time. But the combinatorial optimization problem which we are doing, like whatever I gave you is like very vague, and like this is the meta theorem in the sense that this does for every covering and packing in this set of constraint. But if I fix a problem, I will be able to do much better at time. Okay, so we'll leave this, and if not now, we'll see at 2 o'clock how to do this. Okay. Okay. But now I want to do set cover. I didn't want to rub this for regions. What was the return? Okay, we'll get to that later whenever I have to go. Okay, so now what I would like to do is do a normal set cover greedy algorithm using multiplicative weight of data. Okay, so so what is greedy algorithm? What is a greedy algorithm for set cover? Unweighted set cover. Okay, while universe is not covered, while universe is not covered, pick a set that maximizes the uncovered elements. That's it. This is the end of it. Okay. So now if I write an LP, how do I write LP? As again, minimize excess for all E in E, summation excess, E belongs to S greater than or equal to 1, excess is element of 0, 1. Right? This is what I want to give feasible solution to, like I want to pick some sets. Okay. Notice that it's so annoying. Let xt be the solution returned by the oracle on W1T by phi t. Okay, and we let this was the second step. Let MIT equal to AI xt minus bi divided by rho. And third, weight of I in t plus 1th round is this. Okay. But look, what did we assume here? Z equal to n. We always assume that eta is half. Okay. So I have only given you analysis with eta equal to half. But for this algorithm, I'm going to choose eta equal to 1. I'll tell you why. So if I choose eta equal to 1, then what is this? 1 minus mi to the power t, right? That's the reason. So my weight update for eta equal to 1, my weight update becomes, you will see more clearly what beautiful things happens here. Right? This is what happens. Okay? Rho is my initially weights are 1. Okay? What is the initially weights are 1. What will I pick in the first round? This is my probability vector, right? No? I can pick any set. In the first round, I'll pick any set. Does it matter? I'll pick any set. Right? But this is also in my hand, no? So I should also change this. I don't want to do any of it. Like, it's up to me, right? I will do analysis. Okay? So what will be my cost vector? So what is mi of t? It's a cost corresponding to constraint I. Right? So what should I do? This is very easy, no? Let's define cost of the constraint corresponding to, okay, cost of the constraint corresponding to element I for a given set Cj is 1 if I is in Cj and 0 otherwise. Okay? This is what it is. Do you understand what is the meaning of this? Basically what I am saying here is that, look, if this element is covered, then what is its cost? 1, 0 otherwise. So what do you mean by AAIX by transpose minus PI, right? So I am just trying to, cost of the constraint corresponding to element I for a given set Cj is 1 if I is in Cj and 0 otherwise, right? So what is algorithm going to do? Algorithm is going to pick some sets, right? Some sets, that's my current solution. What is it doing? I have some current solution. I look at whether I am over satisfied or under satisfied with respect to my current solution, and I update my solution, update my weight. So what will I do? I will look at my current already selected set and I say, hey, if I'm already been hit 0, like then my cost is 1, 0 otherwise. Like you still need to hit me. Do you understand this point? Look, what should be the cost of a constraint if it is satisfied? Like it should be more, right? Because I don't want to hit him again, right? Or I don't want to satisfy him again. So if I have already selected some sets, right? So if I'm trying to solve this ILP in this method, what is my partial solution at n? Like what is my solution at some step xt? Is like for some x's I have 1 and 0 otherwise, right? So it means I have selected some sets and not selected some sets. This is what it means. So now I have defined the cost of the constraint corresponding to element I for a given set Cj is 1 if this belongs to 0 otherwise. So what will be the cost? Mi of t, I look at if it is hit or not, right? If it is covered or not. If it is covered or not by x of t. Covered means 1, not covered means 0. That's it. This is my cost. No row vector, nothing. Okay? You will see that like row is 1 actually in our setting. In the setting which I am, the oracle is 1. I'll tell you how. Okay? Like look, oracle is in my hand, right? How, and this row was with respect to this oracle. And my oracle is what is going to return to you? I am going to return to you set. So now what is a set with the best weight? Why? Because look at Wi. What is this Wi now? Is 1 minus whatever it is, 1 minus mi of t. So what is this Wi tells you? Either this constraint is satisfied or this constraint is not satisfied. Either this, if this element I is covered, what is mi of t? 1. Look, if it is covered, then the MIT is 1, 0. So what is the weight of an element, or what is the weight of the constraint that needs to be satisfied? It is 0, right, if it is already covered, and 1 otherwise, right, 1 otherwise. So this is what it is. Okay. Now What we needed to do, so what is my probability vector at this point of time? So-called probability vector is going to be, what is my weight vector? 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 Huh? My weight vector is a 0, 1 vector, right? Is a 0, 1 vector. Think, right? Is a 0, 1 vector. Do you agree to this? My weight vector is a 0, 1 vector. And what is his weight? Look at element E1, E2, En, right? Because that is what I'm writing constraints corresponding to. So if that element is already hit, what is his weight? 0. If it is not hit, 1, right? Okay. Now, what is my probability vector at this point of time? My probability vector is nothing but, it is a uniform vector. My probability of PT is uniform vector, like uniform probability over uncovered element. Right? Now, let's look at what we were doing. P transpose AX should be greater than or equal to P transpose B, which is 1. So we can forget this is 1. And eventually, what the equation did we write? Eventually, equation we got all S, X of S, P of S is greater than or equal to 1. Right? Now P of A, like now this is what my equation is. So what will I pick? Which is the highest weight? Sorry, which has the highest probability? What does it mean if it is uniform probability? It means it has the highest number of element. Right? For that set, you set 1 and 0 otherwise. Now let's look at each constraint. Is it satisfied or not satisfied? It is satisfied. Each set is satisfied. Like each constraint is satisfied. Like why? Well, look, this is what I set. Now look at, but what could be the problem? What? Fine. So look, this is one way of setting MIT, right? This is one way of setting MIT. There could be very many. So fine. So you have to set excess equal to the cardinality of elements which it covers, the highest number of cardinality, and 0 otherwise, because you are, look, what are you trying to do in any round? Like at any point of time, you will run this algorithm several times, right? And return the minimum which comes among this. So suppose I have guessed that this is L. I'm in this round where I have guessed that this is L. Okay? Then I have to set these things accordingly, right? It is not only about satisfying this, right? I have to also satisfy this equality constraint. This is equal to something, right? But at any point of time, I will be picking a set which covers the maximum number of elements at any point of the time. People don't teach this because it is useless to teach this algorithm. But okay? So if you write down, I'll tell you something, right? What is mt.pt? For this proof, what is the cost in this? What is the cost mtpt in this? This is going to be equal to max over f summation pi I going from C. Do you agree? No? Look, either what is empty? Either it is 1 or it is 0. Agreed? Where it is 1? Hmm? What set did you choose in teeth round? One that maximize thing, right? Lose. Huh? So you have that, this is exactly what you did, maximize the C for this. But what does this implies? This will cover at least 1 by opt fraction of the total number of elements. Look, how to say this? Okay. So in round T, what are we choosing at every time? We are choosing a set C which maximizes the number of uncovered elements. Do you agree? Which maximizes the number of uncovered elements. This is what we are choosing all the time. Now, and then we defined what was empty, basically all the elements which I put for those, what is empty is like 1 and 0 otherwise. Okay, so let's write it down explicitly. See, opt covers all the elements. Do you agree? So you fix any probability distribution, right? What happens then? Then one set must cover 1 by opt fraction of those elements, whatever may be the probability distribution. Okay, or maybe let's not even solve this. Okay, I don't care about minimization. Okay, all I will do, I'll set up my weight functions and everything. I will not, so that my is 1 minus 1, so this rho is like 1 minus 1. Okay, I just don't care about L. Okay, let's follow this algorithm itself. Okay, this will automatically come into the play the way we are setting up things. Okay. Okay. Okay, so let's see what happens. So by our choice, right? By our choice, what happens? by our choice, this is always what do you call uniform distribution over uncovered elements, right? This is an uniform distribution over uncovered element, right, in the beginning. Now, so in the beginning, let xt be the solution returned by the oracle on this vector. So what will the first set will return? Anything? What do we return in the first set? Yeah, this is fine, right? Because what will the solution return by this with respect? So now I have xt, so I have pt, I have a should be greater than equal to x should be greater than equal to 1, right? What is pt is 1 over n at this point of time, okay? So what does this imply? It implies, if we look at correctly, then this is like p of s, x of s should be greater than equal to 1, right? And then we argued that we can choose xs, we can choose that set which has the highest probability mass, right? And which has the highest probability mass, because it is uniform distribution, it is, and this is always going to be like this, so it is always going to be covering the highest number of, like covering a set which covers highest number of uncovered elements, okay? So up until then it is fine. Now what I'm saying to you, but I also have a cost vector. What is my cost vector? So the cost vector, because if you look at the proof, what was the cost vector? What was the cost vector? Right? So whatever constraint, so let's write down what is mt times p of t, right? So in the beginning, what is my m of t? First round. First round, what is this? Look, you picked up some set, right? It means for those elements, say E1, E2, En, in that set, you have put 0, right? Because this guy has it. What is this? AIX minus PI, right? So this, since I have picked up a set at that point of time, this quantity is how much? Is 1. For those sets which I have already covered, and minus his 1. So this is 0. And what about other guys? What about the other guys? The other MIs which you have not covered. This is 0 and this is minus 1. Okay? Okay. So the elements which are not covered, so elements which are covered will get 0, elements which are not covered will get -1. Okay. Okay. So what will be MT times PT? So MT times PT will have no contribution from all these guys, which elements are which are covered, because those are 0 anyway. And for else, why he's saying, I thought that I understood this. Maybe I shouldn't be applying this algorithm, multiplicative weight algorithm. Okay, we should not apply the LP based, because this is for LP. Okay, we should just apply just our own multiplicative weight algorithm, the one which I developed prior to this, because this is for some LP and blah blah blah. But we also made an algorithm which is just multiplicative weight algorithm, where we never told you how to get MTs and this, which I only told you for the cost, right? So the algorithm that was, let me write it down. I don't think we shouldn't be implementing this algorithm. This is becoming bogus for me. Okay, but leave it here. Okay, so that also had that had a very different kind of guarantee. So what we did is that first step remained the same. So what you do is that you don't say let xt be the solution returned by this. You don't say. Okay, so you basically say, I'll tell you what it means. You basically say choose an expert I with probability proportional to this. Okay, choose an expert I with probability proportional to this vector, and observe the cost of the decision, right? So we said here, leave it here. We said observe the cost of the decision. Okay, and then we were doing this. Okay, so now let us define our own way what is a cost vector is. Okay, not in AIX or nothing. Okay, so in the beginning my probability is same. I have to define weight vector, I have to define the cost vector. It's my hand. So what is my MT? I just define MT as 0 or 1. What is MT? What is my MT? All those guys covered, put 1, uncovered, put 0. Sorry. Yeah, it's penalty, right? So I covered, I put 1, and uncovered, I put 0, or maybe the other way around. Let's see. Help. We know algorithm, we are just trying to apply this algorithm in our setting. We know greedy algorithm, right? So what's the big deal? Yeah, so covered should be 1 and uncovered should be 0. Because otherwise weight, if this is not what it is, because eta is 1, it cannot be, look, weight cannot be 0 if I do not penalize uncovered people, right. So this is how it should be. But now let's look at, so this is what my empty is here. So I have chosen a set, made this and this. Now what is my expected cost? Expected cost was empty times PT. Okay. What is that? Now if you notice, what is this? Look, all the in the beginning, look, I had some PT, right, where definitely at the places where they were 1, look, it is a uniform distribution over what? Look, what is PT? PT is going to be some zeros, and look at the step before this, all uncovered elements. All uncovered elements until round t minus 1, right? At all those places, suppose this is some z number of elements. At all those places, this pi will be 1 over z, 1 over z. But clearly, at all those places where which I have selected in this round, am I right? So if I apply mt.pt, what I am going to get? All other places, even if, look, either this is positive or this is, like, all the sets which are already covered, already covered, anyway both places are 0, so they do not contribute. But look at other places which is still not covered, this guy is going to put 0. So even if the corresponding guy will be here positive, this guy is going to be 0. So what is left here? It is left exactly those places which are covered in this round, right? Because see, what is the PT vector? PT vector is this. So this is the distribution with respect to how many elements which are covered up till round t minus 1. For example, look at round 1. Look at round 1. Round 1. What is all this? 1 by n, 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 1 by n. But what is this vector? Whichever set you have covered, you have put 1, 0 otherwise, right? So you delete all those. So what you have left, this is exactly what is left is maximize over C, okay, I in C, PC. This is what, this quantity and this quantity is exactly the same because this is how you chose your PT, right? Okay, so now this is clear, right? So what happens? We have to think. So probability distribution is on all the elements which are uncovered from the previous round. An empty vector gives 1 to those elements which are covered in this round and 0 to otherwise, and hence the only places where mt.pt can be non-zero is exactly those elements which are covered in this round. Okay, good. Now it makes more sense. Otherwise, like, I was completely confused what is happening here. I thought how different will be from fractional set cover, no, but it is very different from fractional set cover. Okay. So what can we say about this? What is this? Can I say this is at least 1 over opt? Can I say this? Imagine the current opt which covers all sets of elements. Opt covers the all elements. So at least one set there must be which covers 1 by opt number of elements, right? So if you look at that probability mass of that set, it is at least going to be 1 by opt, no? Look, opt is going to cover the current set of, say, z elements, right? So there is a set which covers how much? Z divided by opt number of elements. Agreed? Z divided of opt number of elements. Now what is the probability mass of Z? probability mass, like there exists a set S such that it covers at least these elements. What is the probability of mass of S? Probability mass of S is definitely going to be equal to it is Z, right? So suppose it covers Z over opt element, and suppose size of S is, so it is going to be 1 over S times Z times opt, like it is going to be at least 1 over S, no, it is going to be 1 over Z times S, right? There are mod S elements in that set, and there are total number of elements is Z, so the probability of each element covered is 1 over Z, so this, right, mod S bata mod S divided by Z. So this should be equal to, I want to say that this is greater than equal to 1 over opt. This is what I want to say. But that is okay, because why? Mod S, see, look, so what do we know? Cardinality of S, no, this is correct, right? Okay, so now what is Z? Number of elements which it covers, and mod S is his cardinality, so this is his probability mass. Now what do I know about mod S? It covers at least Z over opt elements. So this is greater than equal to, right? Mod S is definitely greater than equal to Z over opt, because it covers 1 by opt fraction. So I replace this. So what will I get? 1 over opt. So this is why this is at least 1 over opt, right? Irrespective of whichever probability distribution you choose. Okay. Okay. So let's just wait. I took way more time, but fine. Are we done now? Okay. So if you would have followed the analysis of this, like I don't. So what happens is this. I'm just giving you. I mean, please don't know this algorithm. It is okay. So what happens is that the potential function, which was, what is potential? It is sum of these weights. What we were able to show that phi of t plus 1 change is equal to phi of t, this is what we showed, times 1 minus eta times mt times p of t. This is what we had showed last time. Okay. Now what is this? This is less than equal to phi of t, eta is 1 in our case. Okay. So this is basically, it is 1 minus x, right? So 1 minus x is less than equal to e minus 1. No, e minus x, right? So I apply phi t, then what will I get? E to the power minus eta mt times pt. But eta is 1, so let's forget this, which is equal to phi t times e power minus 1 over opt. Okay? And this, actually this is a strict inequality, because like, what is that called? Not this. This is a strict inequality, right? When you have uncovered elements. Look, you are substituting this by 1 over opt, right? So even if you have one uncovered element, this is a strict inequality. This is not, okay? No, what I am saying, this is a strict inequality. Strict inequality when I replace this with eta over opt. This is strict inequality. So what do you know? Even if there is one element, how many times do you drop? What is a fraction by which each time the potential drops? Huh? Drops by factor 1 over E times 1 over opt. Right? So that's the so we run this as long as some element has not yet covered, right? So you run, so this is what I do. Look, this is my weight update method. So I pick up a set, like I'm just giving you algorithm based on this idea, right? I'm not trying to use any, and I did this analysis we have to do all this analysis because all this analysis was only for eta less than equal to half, but we chose eta equal to 1, so you have to do it all over again, right? So clearly ln n times opt iteration suffices. If the number of iteration this guy goes is ln n times opt, then you will not pick more than ln n times opt sets, because each time you pick one set and that's it. Okay, so the upshot of the story is there are some general meta theorem, but we can take the analysis and all this and design even like some sort of rounding algorithm for many of them. So this is the upshot of the story. Okay.